Hi everyone. Let's practice the things that we need for ANOVA. This should be a pretty short, pretty simple video because you did a lot of this last week. And so hopefully you'll be able to just zip right through this. Please write to me if you have any questions about anything that doesn't seem clear or is not working for you. I know sometimes the remote lab doesn't work and, well, we just try to survive it. That's all I can say. One thing that I wanted to show you that's new in these more recent editions of SPSS is that you actually can fill in a role for your variable. And that wasn't available when we were talking about SPSS yesterday in class. At least I don't remember it being there. It might have been there and blocked my little picture over here. But this can be really helpful because we can give the title of input to our independent variable. So think independent input. It's the thing that we're putting in, and then target, that's the thing that's coming out. And that's actually the thing that we're targeting with our input variable. So for example, here we have a physician prescribing a dose, and the dose is supposed to change the libido, our target variable or our dependent variable. And last semester when I taught, I had a student who all semester long, he kept telling me independent and dependent are the most confusing things. And so different members of the class would take turns giving him ideas and keys for remembering what's independent, what's dependent. Um, and he kept getting better, but I'm not convinced that he totally mastered it because it's kind of mind-boggling. So practice with this. We'll look at your surveys individually, and we can kind of talk about what might be a great independent variable. So something to kind of use for comparisons. Like here we're comparing doses. And then what would be a dependent variable? What's the thing we're measuring, like literacy or feeling safe on campus or feeling anxiety when you're taking a test or reading outside of the required reading that a teacher's got to do. So anyway, we'll keep talking about that. We'll keep practicing that, and don't lose faith. It takes time. Okay, so here's the spreadsheet. Let me go to, this is my variable view. Let me go to my data view, and this is the same one you worked with last week. So it will start becoming familiar. I like this because then field is going to add to this a covariate. So when we do ANCOVA, it'll be the same data. I'm trying to remember. He uses this over and over again so that we'll use it in more than just this demonstration. Okay, so if you remember, come into Analyze here. And here is the compare means that has one-way ANOVA down here. That's one way of getting to ANOVA. But I'm going to skip that one. I would prefer that you come to the general linear model, ANOVA. And here I made a little sheet with output all ready to go. This right here, this first ANOVA is what I get when I just use the compare means ANOVA. And here's my report. I mean, really, I have everything that I need except when I use the compare means, I have to figure out eta squared by hand. And this is in the field book on page 472. But see, I have to take the 20.13 from my sum of squares and divide by the 43.73 to come up with this 0.46. Well, watch what happens if I go into this second option for ANOVA, which is general linear model. And this is where we'll want to be to do ANCOVA. This is where we'll want to be to do factorial ANOVA. So this is a powerful place to go. In this course, we're using univariate, meaning there's one dependent variable. If you take the summer course from Dr. McKim, she's going to talk to you about multivariate, meaning there can be several dependent variables. You can imagine how sometimes, well, the article that we discussed in class, and maybe they wanted to make depression and masculinity both dependent variables together. Is when they're closely related, that'll work. I'm not sure it would have worked for that article. But anyway, let me click on univariate. Okay, so our dependent variable, it's our target variable. It's the thing that we want to change by changing our fixed factor, which is our dose of Viagra. So I'm going to put that here in fixed factors. Skip random factors for now. We can talk about them in class, about what they mean. Likewise, trust me on the post hoc. We will talk about these in class too. We're going to run post hoc tests for dose. In other words, if we find out that this is significant, we want to know, well, which dose, right? There were 3. So to tell me that there's a significant difference, I don't know if that means that my control was different from the other 2. Where are those differences? So I will tell you my favorites. I've noticed that Field likes some of mine, plus he has his own favorites. But I like the Tukey because it takes everything 2 by 2 and compares. So it'll compare control to low, control to high, and then low to high also. Likewise, I like Bonferroni. Bonferroni is very strict. So if you find significance in Bonferroni, wow, you really hit onto something amazing because it's hard to get past the Bonferroni gateway, so to say. Then I also, especially for this data set, like Dunnett. And the reason Dunnett is so good is because when you have a control group, it tests that control group versus the other categories. Now, it automatically assumes that control group is my last category. And so in SPSS, that would be my 3s. And that's not true. If you go into the variable view, you'll see that the control group is labeled as the 1. So I'm going to change my control category to first. Okay, and then I'm going to continue. It'll take me back to my main menu because I'm not quite done. One more thing that will just save you a little time is coming down here into options. And here in options, I'm going to get my descriptive statistics. That will give me my means and standard deviations so I can write this up. And ta-da, here's the effect size. I can get my effect size for free. I don't have to go through like Field did and calculate it by hand. Okay, so another box on here that I often check is the homogeneity test. Just be aware that it's here. We're not going to talk about it yet, but that will help us decide, oh boy, we have a really weird, skewed, maybe bimodal data, and we're going to have to use a different test. Something besides ANOVA, because ANOVA assumes, one of the assumptions is that we have a bell curve. Okay, so let's continue with this. I just had a great thought. Sometimes I like to create bar charts for this data, and I can show you how to do that. But look, right here under plots, I can get a graph for free. I'm going to put dose on my horizontal axis. So that's horizontal, that's my x-axis, and that makes sense. The dose, the independent variable, tends to go on the horizontal axis, and then the dependent variable, the thing that results from it, tends to go on this y-axis, the vertical axis. Okay, so I'm going to add that. This is one weird thing about SPSS, and you're probably getting used to it. I've put this in the box, but nothing will happen until I click on add. Okay, it just added dose to my list of plots. Now I'm good. But until I added, I wouldn't get that plot. Okay, continue. Click on OK. And ta-da, here we go. Here are my means and standard deviations. Here's my ANOVA table. Now, when we did the table under the one-way ANOVA compare means, it was actually labeled ANOVA, whereas now that we've done it under the under this right here, we did it under this general linear model univariate. It's hard to remember. We call it GLIM sometimes, GLIM. Now we get, oh, excuse me here. I'm going to make you seasick. Sorry, everybody. Now we get this. This is the ANOVA table, but instead they label it tests of between subjects effects. I don't know why, but that's okay. This is the ANOVA table. Please do not put this table in your paper. In Huck's chapter, he actually shares part of a paper in which the authors include the table. And I have seen journal articles that include the table. There may be one or two journals out there that encourage or allow that. But the way I was raised in statistics and most things I see say absolutely not. This table should not be in a paper. No one needs to know the sums of squares. Like the intercept sum of squares is 180.26. That doesn't mean anything to anyone. It's meaningless and it shouldn't be in a paper. It really shouldn't. So what I've done instead is to copy for you into this Word document the things that should. And so hopefully you'll be able to take this Viagra example and translate it then into the two other spreadsheets that I've given you for the homework. 1 page, 1.5 pages each. Okay, the other thing now, remember I asked for Tukey, for Bonferroni, and for Dennett. And here they are right here. And in just a minute, I've copied and pasted these into a Word document. I'll show you what to pull out. You can ignore this homogeneous subsets. This just kind of shows how they compared, right? So this mean to that mean, this mean to that, this to that. Okay, here we go though. This profile plot, this is the graph I asked for. This is fantastic. I would like you to put one graph in your paper, and this would be a great one if you'd like to use this one. It gives a nice representation of the placebo moving up to the low dose, moving up to the high dose. So visually, just looking at the graph, we can see a difference. I mean, they're not all the same. This is not a flat line. Now the question is, statistically, will there be a difference? The other graph that you might consider making, let me come in here to the chart builder. There's kind of a nice option for doing a bar graph. And you put the bar graph right here. And then you put libido onto the, well, let me put the dose first. I'm going to put the dose on the x-axis. So this would be the same place that it is here, right? Dose of Viagra across the bottom. And then libido, I'm going to put in here. If I don't put libido, it'll just tell me that there were 5 in the placebo, 5 in the low dose, 5 in the high dose. But by putting libido in here, it's going to calculate the mean for each group and give me this bar chart right here. This bar chart basically gives the same information as this line chart here, right? So here's this mean at about 2.2, here's this one at 3.2, and then here's this mean at 5. So you see the mean climbing as the dose goes up. Well, let's look at the bar chart. 2.2. Here's 3.2, and then here's 5. So once again, the mean is climbing as the dose goes up. So either one would be great. Feel free to put one or the other of these in your paper. Okay, so here I've started writing this paper, right? And here's what I've got. Here's what I'm thinking. So you give each of your papers, you'll need to do 2 of these. Give each one a title and give a little teeny reference here. I cited Drugstore from 2016 and tried to tell you, my reader, why this might matter, and to come up with a research question that kind of goes along with why I think this matters. Here's my method. I had to make up a little bit of information. I decided to pretend like these males were between 50 and 75. And then here are my results, okay? So where did I get these results? Here I have a mean and a standard deviation for each one of my groups. Okay, well, I got those from this output. Here's this output from the compare means one way ANOVA, and then here's this output, same thing, from the general linear model ANOVA. So I take this. You could, if you'd like, put this table in. Make sure you make it APA style. Remember, no vertical lines at all, and then only 1 or 2 horizontal lines, maybe under this dependent variable and under the total. You can look in the APA manual for some good examples. But I chose not to put the table in. I just chose to write these means into my write-up. So here they are. And then I discuss doing the ANOVA procedure and seeing if those means are different enough to be significant. And here's how I reported the output right here. So once again, let me go back to what came up on our output. So this is the output that came from, let me just actually, this is the output that came from the compare means, but I'm going to just go ahead and copy this and paste it down here. So I've got it right next to the output that we get from the linear model. Actually, I'm going to have to paste it over here so you can see everything. Okay. Okay, so right here, my F in italics, and then I put these in parentheses. Notice that the research article I brought to class yesterday actually had these as subscripts. So you could go up here, hit this little subscript font. See how there's the X and the little subscript? You could put 214 down there. Either one is acceptable, but like the article I just sent you, different journals will want it different ways. So get to know your journal and do it the way other published authors do it. So here's where I get these degrees of freedom. This degree of freedom 2 comes with the dose, and this degree of freedom 12 comes with the error. I occasionally, and I did this one time in front of class, I get confused and I think, oh, it's the corrected total, it's 14. That is not right. So just steer yourself away from that corrected total. The truth is 2 plus 14 will add up to the corrected total. Oh, do I have 14 in here? What am I doing? This should be 12. See, there I go. Oh, I'm so sorry. The F should be 2, comma, 12. It should be dose and error. And then these two add up to 14, the corrected total, but we don't type the 14 in here. I can't believe I did that. See, I told you, I get confused about this. So say, I am not gonna do what Jenny did. I'm gonna get this right the first time. Okay, then we put the statistic, remember with 2 decimal points, so 5.12. And then we put the P, italicized P equals 0.025. Then I want to put eta squared. Instead of having to calculate it by hand like Field did, I just pull it right off this chart right here, 0.46. Okay, and in the paper then, I go ahead and explain that that eta squared is, oops, let me pull up my paper here. That eta squared effect size is moderately large. And you can look in the Huck book. He's got about 5 or 6 different ways of measuring effect size, and he's got a scale for each. What would be considered small, what would be considered medium, and what would be considered large. And ours is on that large size of medium. And so that's why I put that here. You can use the kind of wording that you'd like, but go to Huck for pretty nice, he's got a nice summary there of some of the effect sizes people use and how you can determine which ones are large and which ones are medium. Okay, then I've got right here one more. I actually put these in a compound sentence. It might be better to have each of these as a separate sentence, right? Because this is an effect size. I'm just thinking now as an English teacher. And now this is another thought. This shouldn't be joined necessarily. The statistical difference was between the high dose and the placebo. My Dunnett's post hoc test, the probability was 0.015. So let's just go in now and let's look at these tests, okay? Where am I getting this? What am I talking about? Right here, these are the post hoc tests that I asked for, the Tukey, the Bonferroni, and the Dennett. Should I report all three? No. I asked for all three so that you would have a chance to look at them and think about them, but I knew before I even started this experiment that I wanted to have a control group and that control group meant that the best test I could do was Dennett. If you've got a control group, do a Dennett. Now, I know for your own research, you don't have control groups. Instead, you're going to be doing ANOVA based on your demographics, like my undergraduates versus my graduates, or my English-speaking audience versus my English as a second language audience, or maybe males and females, right? Something that simple. Then you would either need to use a Tukey or a Bonferroni. And I just wanted to show you quickly, remember the smaller the p-value, the better. Like, wow. So Dunnett gave us, for this high dose placebo, they gave us the smallest p-value. This is cool. I like this. Bonferroni, remember, that's the toughest test to pass. Like, that one's really tough. And so sure enough, this is the highest p-value. And once again, it's high dose placebo. So it's telling us the same story. Placebo, high dose. 0.025. And then here's Tukey, a little bit in between the two. Not quite as good as Dunnett, but a better p-value than Bonferroni. It's a little bit easier to find something significant in Tukey. And so I'll be honest, I almost always do Tukey in my own research. Tukey's research is very well respected. He's awesome. My neighbor, who's a statistics professor here, named his dog Tukey. Okay, that's his claim to fame. Okay, so once again in Tukey, notice placebo versus high dose. Yes. High dose versus placebo. Yes. So see, any significance that's over 0.05 means there was no statistical difference. So was there a difference between the low dose and the placebo? No. No. Was there a difference between the low dose and the high dose? I can come right here, low dose versus high dose? No, no. And all of these tell the same story. Low dose placebo? No. Low dose, high dose? No. Same thing here. Low dose placebo? No. In this case, Dunnett doesn't even test low dose versus high dose. And why is that? Because he actually knows that we want to compare everything to the placebo, which actually, oh my word, as I'm talking to you, I realize I'm not sure Dunnett's is my best choice, because here's what I wrote in my paper, okay? So this is how I chose to frame my research. I chose to say that sometimes doctors just prescribe the high dose, even though there are side effects. And I think that possibly the low dose will be just as good without the side effects. So my whole premise in conducting this research was really to compare the high dose to the low dose. And I had a placebo group just because always, if you can have a control group, it's a better experiment. So for that reason, I actually should not do Dunnett's here, because Dunnett's means I'm really focusing on my control group. And actually, I think I'll do Tukey. Remember I told you I like Tukey? Okay, a Tukey post-hoc test, but now I have to change this p-value to 0.21. But that's actually better because Tukey looked at all the pairings. Tukey included low dose to high dose. Why am I not reporting low dose to high dose? Because it was not significant. So anything in here that was not significant, I'm not going to report. If I started reporting all these numbers, my reader would die. I just pulled out of here this one number because it's specific to my test and it's significant. I should probably on this write-up add a sentence because my research question is, does the high dose of Viagra offer greater impact than the low dose? I should just say there was no statistical difference. Sorry, I cannot talk and type at the same time. Okay, I answered my research question, no difference. Okay, now this is something, oh, they don't even have statistical here. Okay, this is something that does come up. There was no statistical difference between low dose and high dose, but look at this. It looks kind of like a difference to me, right? I've got this graph. Make sure you reference your graph. I put right here, figure 1, and I need to label this, don't I? Figure 1. And remember to maybe put notes, maybe actually for a graph, figure 1 goes on top. Oh gosh, APA style might be the death of us, but that's okay. We're gonna do this right because it's great practice, just like the piano. Okay, so here's my figure 1, give it a title. Now, in my conclusion, I say the results of the experiment suggest that there's no difference between low dose and high dose, right? Statistical, boy, I'm sorry. TIS. I just keep misspelling that. Okay. So this result might allow physicians to prescribe lower doses. However, these sample sizes were so small that I feel like further research is necessary. I think this study missed the difference. So anytime that you cannot reject the null, you can't say, well, couldn't reject it. We're done. The null stands. No, no. And the reason is because before we even conducted this ANOVA calculation, we assumed that the null was true. If you assume something and then you say, well, I guess, I couldn't really find anything different, that means whatever I assumed to start out with must be right. That's not enough of a case to say, yep, we have definitively answered that question. Instead, when you cannot reject the null, you say, we need maybe it's bigger sample. In this case, it is, of course. Maybe it's we've got to account for some of these confounding variables. Maybe it's we need to be more careful in our sample. Like if we test, so I assume that these were 50 to 75-year-old men because they tend to take this medicine. If we test it on 18-year-olds who really, the medicine was not created for them, then maybe we've got a bad sample for this type of research and we can't say anything about the people who really need to know. So there's so many ways that we may have missed a significant result because we didn't do our experiment quite right. And that's why, at least in this case, it's really important for me to say we need to do more research. That isn't the end. That isn't really the answer to our question. Okay, so this is kind of my write-up. It's actually 2 pages because of the graph, and I'd like you to do 2 of these. So you can submit them as separate documents. You can upload as many documents as you want, or you can put them together into one document. And just kind of follow the pattern here. I'll post this and my output and the Viagra spreadsheet. And just have fun with it. Good luck. Thank you, and bring any questions you have. Just post them, email them, bring them to class, you name it. Have a great week, and thanks for watching the video.